Okay, so this is just a follow-up to a video I posted a while back. It's an algorithm I wrote to lay out arbitrarily sized rectangles. And so what you see here, I'm in a browser. I tossed 150 div elements into my special algorithm container, and I gave them all numbers. And any of these divs can change size at any time that they want. That's not necessarily a part of this demo, but assume that that's the case, right? I'm resizing the window here to any size that I want, and it's repacking everything, relaying everything out. It's fine. Nothing is overlapping. Everything is uptight and close together as it can be, while at the same time maintaining its order as much as it can maintain its order, despite packing everything up as tight as it can be packed together, right? So it's kind of a juggling act to get something like this right, because you want the top left div to be the first div that you toss in. You want the top left, the div right next to it, to be the second div that you toss in. And so that tries to maintain this, but you notice 23 is up here, right? 23 is up here because look at the size of 23. It makes sense right here. It makes sense right there because that's like it fits. That's part of what makes this work. You need to be able to account for these elements that are further down the road, making sense higher up in the grid. And so that's what it tries to do. And so it does it pretty quickly. How it actually does it, we can bring up this little diagram. Okay, so initially what it does, it'll do something like this. It will pack everything. You give it something like this, which is essentially, okay, well, here's 5 rectangles. It's going to take those 5 rectangles and it's going to pack them up at the top left, and it's going to go left to right until it gets to the end. And then it's got this 5th rectangle. It's going to go over here and it's going to pack it right here because that's the best place to pack it that it can calculate, right? So it's going to do that. It's going to determine that, oh, hey, I was able to pack the rectangles into this height, okay? And then it's going to say, okay, well, now maybe I could do something with that height, right? And that would be the equivalent of, okay, well, we're going to ignore this stuff from now on, right? And now we're just going to try and space it out here. Let me try that again. We're just going to try and space it out here. We're going to center these. We're going to kind of space this out just a hair more. We're going to space this out just a hair more. And we're going to space this out just a hair more. We can't move these guys up and down, though, because they're touching the ends of the grid, right? So we're going to try to arrive at this visually pleasing layout. That's the goal here. I'm going to undo all of that. And just to illustrate how this works, so it's going to do that, and as part of that, it's going to end up with some kind of grid right here where it's like trying to figure out how to space things out. And the way it's going to figure out how to space things out is going to create 2 binary search trees. One is a big binary search tree across the entire x-axis, where each node of that search tree is some interval across the x-axis. And in that interval, there are going to be multiple intervals across the y-axis. Those are actually going to be nested binary search trees. So we're going to have 2 main binary search trees, and each binary search tree will itself, for every node, contain another binary search tree. So we'll have one big one here, and we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever search trees right here, and we'll have one big search tree right here, and inside of it will be another 9 to 10 binary search trees inside of it. And essentially what that will do is allow us to maintain a model such that we can update the positions of these rectangles quickly and without any rectangles colliding with each other. The entire time we're able to just search across these binary search trees in order to figure out, for example, how far the more accurately, how far this green rectangle can travel in the y-axis, right? So these binary search trees will give us that information quickly. They will also give us this information quickly, which means we know how far we can shift any one given rectangle, either left, right, up, or down. And while we shift those rectangles left, right, up, or down, we update this model. And that amounts to login update times. So we aren't login retrieval, login querying, and login update. And where in is not the number of rectangles here. It's that would be the number of unique positions across any given axis. So here we're going to be bound up by how many unique minimum and maximum values each rectangle has. So right here, these two are sharing a value. So that's going to decrease the complexity of our algorithm. This one right here, this blue rectangle, it's causing more complexity right here because it's ending right here. It's not sharing that ending with anybody. So that's where the complexity comes in, and same with the other axis. So right here, there's going to be a binary search tree that only contains one rectangle. If we look at this little interval, if we look at this interval, oops, I didn't mean to drag that. If we look at this interval, we're gonna see two. It will contain two rectangles. So yeah, I don't have any with 3 rectangles, but hopefully that kind of makes sense. Ultimately, you kind of end up with this, with 2 binary search trees containing a bunch of binary search trees, and then you use that to iteratively reposition things such that they look like the example in the beginning of the video, right? Where I packed all of this stuff up here and then I spaced it out nicely, right? So this ended up here, and then I grabbed all of those and spaced them out nicely. Now I'm screwing everything up. It's okay though. That's the end.